compare what you got with what I got. If you've got any comments, questions, concerns, queries, conundrums, or consternations, yes, Malik? You mean if it goes CHOH2 or CaOH2 plus Na2S? Doesn't matter. It's like 1 plus 2 is the same as 2 plus 1. They both equal 3. 1 plus 2. 1 plus 2 is the same as 2 plus 1.
Yeah, but like you said it so fast. Like,
I know, that was kind of on purpose. It's kind of on purpose. Comments, questions, concerns? Any issues? Panit, I posted the videos from, I don't know if you saw them, but they're all up now. Going once, twice, thrice, sold. Okay, cool. We've done 4 reactions. We've done the synthesis, the decomposition. Those are basically opposites of each other. One takes 2 simple things and makes a complex thing. The other one takes a complex thing and breaks it down into simpler things. We looked at the single replacement, which takes a singleton, an ion, or a polyatomic ion, or a single atom, an atom of an element, and it reacts with a compound. Depending on the charge on that atom, it'll either swap out with the positive or negative portion of the compound. Then we've looked at the double replacement. The double replacement's easy. They're each partnered with something, and neither of them are happy with their partner, so they swap. I'm sure there's a relationship example in there, but I can't think of one. And now we're going to look at type 5, which is the same type that we've looked at several times already, the neutralization reaction. Neutralization. Here we go. A couple days ago, we talked about these. Tell me about them. A neutralization reaction requires what? An acid and a base. Very good. And the products of an acid-base reaction are always what? A salt, you betcha, and water. So the general formula for this, I could give to you as the same general formula I gave you for acids and bases before. The general acid is going to be HA, the H because acids are hydrogen donors, A for acid, plus BOH, OH because bases are hydroxide donors, and B because base. And these guys are always going to create H2O, or HOH. Take the hydrogen from the acid, the hydroxide from the base. HOH is just another way to write H2O, which is water. And a salt. Now, the generalized form for the salt, given the generalized formulas here of acids and bases, is going to be what? BA. I don't know who said that, but they are correct. It's going to be BA. B is the positive portion of the formula. A is the negative portion of the formula. So it goes in this order. And an example that I've given you before is this guy here. HCl plus NaOH is going to produce NaCl. In this case, the salt is a specific salt. It's table salt plus HOH, which is just water. So we've looked at these before. I'm not going to spend a ton of time on it. You guys should be able to crank out these 4 for me right away. The first product in all 4 of these reactions we could write as what? Water. So H2O all the way down. H2O, 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 H2O. Plus, 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 plus. And now let's go ahead and build the salts. What's the salt coming out of this first acid-base neutralization reaction? It's going to be NaBr. Whoever said that is correct. The charge on sodium is +1. The charge on bromine is -1. So you just need one of each to balance each other out. How about the next one? The water is there, and now what's the salt? Sorry, Josiah? Oh, sorry, I thought you started speaking. Yes, Mg. Mg2 PO4 in brackets 3. She's correct. Number. Why are you correct? How'd you do it? Okay. Magnesium's got to have a +2 charge. The phosphate's got a -3 charge. So you're going to swap and drop these things. The positive ion always gets listed first. The negative ion comes second. So we're going to get Mg2 bracket, no, Mg3 bracket PO42. We have to swap and drop, not just drop. Okay, what's the next one going to be? We've got the H2O. What's the salt? It's going, you suggest it's PbCl2. Why is it PbCl2? Lead is multivalent. It's got different charges. How do you know it's +2? Because OH has a charge of 1, and there's how many? 2 of them. Good. So lead's going to have a charge of +2. Chlorine's got a charge of -1. So that salt's going to be PbCl2. Very good. And then the last one, Al, and then then the ClO4 in brackets 3. Very good. Aluminum's got a charge of +3. You can see here that the polyatomic ion ClO4 has a charge of -1, so we need 3 of them to balance out the aluminums. Acid-base neutralization, something I introduced to you, what is it, 4 days ago now? 3 days ago? Monday. Tuesday? Earlier this week. Flip the page. And now you got the last one. We've done the synthesis, decomposition, single replacement, double replacement, neutralization, and now it's everyone's favorite reaction, the combustion. Now, combustion reactions don't always look the way you're probably all picturing right now in your head. Some of them certainly do, and they're really cool. I'm going to demonstrate probably what you're picturing, and it's going to be really cool. But I'm also going to demonstrate something really boring that happens really slowly, that while it looks cool, is certainly not nearly as entertaining. But they're both going to be combustion reactions. There's actually a combustion reaction happening inside you right now. It's not explosive because if it were, you'd be dead. But it's happening in you right now all the time. And you learned about it in grade 9, especially if you had me. But every one of you should have learned about it in the carbon cycle. So combustion reactions. Combustion reactions, does anyone know what kind of compound goes into a combustion reaction? Oxygen is one of them. What's the other one? Gas is an example of one of these. Gas, I'm gonna generalize gas. I'm gonna say not just gas, but I'm gonna call it a hydrocarbon. Hydrocarbon. Now, when you say gas, you probably are thinking of what's coming out of the pump when you fill up your car. But that isn't just a singular compound. There's a bunch of compounds there that make up what we call gasoline. One of those compounds is octane. There's an octane rating on the different fuels. The higher the octane rating, the more premium your fuel is. Like premium fuel has a higher octane level than regular or low grade fuel. And that helps it burn at different temperatures. If you have that's high end is not the right word because I don't have a high end car, but my car takes premium. If you have a car that is designed, my car kind of is, a car that's designed for higher performance, they will take premium fuel, and the reason for that is their engines are designed to explode the fuel at higher temperatures. If you don't, then you can use the lower octane fuel. Putting premium fuel in there for you car people, putting premium fuel in a car that doesn't require it isn't going to make anything better. But putting regular fuel in a car that requires premium will hurt performance. So it saved you some money there, perhaps, Josiah. So hydrocarbons are an example. A hydrocarbon is any compound that ends in ANE. So the names will end in ANE. And a hydrocarbon is made up of hydrogen and carbon, as the name suggests. So ANEs, ANE compounds that you're probably familiar with, are things like propane, Use it for gas, or for the fuel for the barbecue. Or another one that all of you are familiar with is methane. Methane is the gas you produce in farts. It is CH4. It's also a greenhouse gas. Methane, there's ethane, propane, butane for those of you who like to have lighters, pentane, hexane, nonane, octane, decane, all these different kinds of fuels made only of hydrogen carbon. That's one. But another component of what you would call gas at the pump, it says include up to 10% what? Those of you who fueled up your car before, what does it say on the tank, on the pump? It says on the pump it may contain up to. None of you have fueled up. Your parents have not made you fuel up the car. They tell you which one to get. 80. Yeah, that's the octane level that I was talking about a second ago. Okay, so fuel pumps will say may contain up to 10% ethanol. Ethanol is an alcohol. It is one of these guys as well. So alcohols also are involved in combustion reactions. Ethanol is an ingredient in what you would call gas for your car. And alcohols all end in OL. So methanol, which I'm going to show you today, is an alcohol. You don't want to drink it, though people used to try. Has any of you ever heard of moonshine?
Yeah.
The alcohol in moonshine is methanol. And in moonshine is super dangerous because, as you'll see today, it's explosive. And methanol in concentrations above very small concentrations will make you go blind, and then they'll kill you. So methanol we try to stay away from. If you go to the liquor store when you're 19 and you go buy yourself some beer, some wine, whatever, what have you, the active alcohol in there is what? Who knows? The consumer alcohol is ethanol. It's the same stuff that we put in car fuel. It's the same stuff that we can consume. The safety of alcohol is certainly debatable because it's a poison. It damages your liver. It damages all of you. It also has other effects that people like to take advantage of. But, I mean, alcohol, ethanol, while it's consumable, also will impair you and degrade the quality of your organs. There's also isopropyl alcohol or propanol. That's the alcohol found in rubbing alcohol or hand sanitizer. Then there's butanol, there's pentanol, there's all the different alls are all different kinds of alcohols. Someone offers you moonshine, politely decline. You don't know who made it, you can go blind and then die. People offer you ethanol. It's not going to kill you, but you're too young. Don't do it. Alcohols, hydrocarbons. Alcohols are made up of C's, H's, and O's. And then there's another one that some of you are way too familiar with and like a little bit too much. They're called ethers. Ethers end in E-N-E. Ethers are compounds, the smelly compound found in perfumes, found in deodorants, found in your body sprays. Any of you who abused Axe body spray, you were... it's the ethers. There are different kinds of ethers have different kinds of scents. You can get different ethers from different places. Ethers are also made up of carbons, hydrogens, and oxygens. They're also very flammable, which is why, I mean, we're listing them here as a combustion reaction. It's why Axe body spray is as flammable as it is. You hold up the lighter, you hold up the thing, you go, and it makes a big flame. If you've never tried that, don't try it indoors. These three compounds all are classified as one type of compound. Does anyone know what they're classified as? It starts with an O. No, because the first one doesn't have oxygen in it. The next letter is an R. These compounds are all classified as a group of compounds called organic compounds. So an organic compound, that word organic has different meanings. When you hear the word organic, you probably think of the expensive aisle of fruits and veggies that all look a little bit worse than the other veggies, and you pay too much for an inferior product. Organic is not necessarily worth it. I've worked on farms, I know. I saw how the organics were produced. I saw how the other ones were produced. Don't waste your money, just buy regular produce. GMOs are fine. A little bit of pesticide never hurt anyone. That's not true. But what about the bugs? Yeah, fair point. But what we mean when we say organic in science class is we mean an organic compound is any compound that includes a large percentage of carbon and hydrogen. There can be other stuff. You can have oxygen there. You sometimes can have nitrogen in there. You can have phosphorus in there. But if the bulk of the compound is carbon and hydrogen, we classify it as an organic. So these are all organic compounds because their primary structure is made up of carbon and hydrogen. Alcohols and ethers also have oxygens thrown in, but the hydrocarbons don't. They're just straight carbon-hydrogen chain. So when you combust, a proper combustion reaction isn't just anything that burns, because I'm going to burn something today that has nothing organic in it. I'm going to try to. It's going to be the most boring reaction I show you, but we're going to try. No. Organics plus oxygen are always going to create the same two products. It doesn't matter what kind of organic compound you use. Does anyone know what the products are? Carbon dioxide is one, and water is the other. And if you look at the ingredients, like the reactants, I'm reacting C and H with O. It's not like you can just bring in other stuff. So the compounds have to be compounds that contain CH and O. The most common ones that do that, carbon dioxide and water. So the generalized formula for these kinds of reactions look like this. Look like this guy here. We're going to call it CXHY. That's our generalized hydrocarbon. It says CXHY, where X and Y can be any numbers. I mean, there are pairs of numbers that go together here. For example, I said methane. The formula for methane is CH4. So 1 carbon, 4 hydrogens. The next one is let's go to propane. Propane is a cooler one. Propane is C3H8. So in propane, the X is a 3, the Y is an 8. So this is the general form for a hydrocarbon, made of carbon and hydrogen, and then these X and Y can be any number. They're going to react with O2. They're always going to produce CO2 and H2O. The alcohols and the ethers have the same kind of formula. It's going to be CXHYOZ plus O2 is going to give you, again, CO2 and H2O when you burn them every time. So if you look down here at the 4 or 5 examples that I have down here, once you can identify that you have a combustion reaction, the products are all going to be what? CO2 and H2O. CO2 and H2O. CO2 and H2O. Skip letter D. CO2 and H2O for letter E. I skipped letter D because I want to draw special attention to it. Letter D is C6H12O6 plus O2. Yes, the products are still going to be CO2 and H2O, but this is a very special reaction. I mentioned at the beginning that you guys have a combustion reaction happening inside you all the time. This is it. The one that you have going on inside you is this particular compound, C6H12O6, plus O2. It's going to produce CO2 and H2O, but this reaction has a name. Does anyone know what it's called? Anyone who had me for Science 9, we looked at this reaction. It is the opposite of the reaction that you guys were all about yesterday, the photosynthesis. Yep, keep going. Cellular No. Starts with an R. So close. E-S. No. There you go. Cellular respiration. Cellular respiration is the opposite of photosynthesis. Plants do photosynthesis, animals do cellular respiration. Photosynthesis takes in energy in the form of light, it takes in CO2, it takes in H2O. Plants need these pieces. They turn around and they produce glucose, C6H12O6, and they produce oxygen, which you take in. Your body, your cells need sugars. Your body needs oxygen, and you turn around and you make CO2 and H2O. You breathe out the CO2, you sweat and pee out the H2O. This reaction is constantly going on in all your cells. Photosynthesis takes in an energy source, light. This reaction produces an energy source. We call it ATP. And that ATP is adenosine triphosphate. It's the chemical that your cells require to keep going. It's the energy that they use. So this guy here is cellular respiration. So we could list this up here as well. Combustion requires organics. The organics I listed before were hydrocarbons, alcohols, and ethers. We could also toss sugars in here. And sugars end in OSE, like glucose, or sucrose, or what are the other oses? Those are the only two I can think of right now. Sugars. So those are the 6 reaction types. Synthesis, decomposition, single replacement, double replacement, neutralization, and combustion. And now I'm going to demonstrate for you most of these. Here we go. So, as you can see, lots of all of you have things out on your desks. I'm going to go through them in order. There's one reaction missing. Anyone see a pair of safety goggles? Okay, so we're going to start with the one that worked the worst last block. We're going to work here. So what I'd like you to do is, if you have chemicals on or near your desks, I want you to clear off your desks. Put everything away. Or out of the way. And we're going to do some science. Get up, move around. Get close to, well, not too close. Get close-ish to this stuff. Oh, shoot. I have to go to the lab and grab one thing. Do I? Maybe I don't. Yeah. Where am I starting? I'm starting right in the middle. I need something. Yeah, I have to go back to the lab. I forgot one thing. Quick. Okay, you gentlemen. I'll be right back. Okay, gather around the middle desks.
Like, you can sit over here, bro. You can sit right here. Like, you can sit right here. Elijah, go on. 200, bro.
I was in my life.
Wait, show me that video. I've never seen that.
It's really bad.
You show me.
Like that was funny.
Yo, dude.
Like I'll be like,
I can never see that.
I was like, oh.
What do you mean, though?
I got into districts for short.
Okay, here we go. Okay. Okay, so synthesis reaction is the first one. This one didn't work super well last block, so we're going to try again, see what happens. I'm going to use steel wool. This is the other plate of steel wool before. You pull up. What's steel wool, so?
I don't know, but I just know what it is.
Well, I'm asking you what it is. That's exactly what
I
I'm
don't know
asking.
what it is, but like I know it.
Yeah.
Okay, steel wool is steel. Steel's made up. Iron.
Iron wool.
Steel is iron.
No.
You can in the form of an SOS pad. You betcha. You take steel wool, you cover it in soap, you get something called an SOS pad. You betcha. You can scrub your pots and pans with this. Don't do it if it's cast iron. Okay, that looks like it might work better than last block. So that thing has a mass. It's 1.2 grams. And let's hope this works better than it did last block. So I'm going to light it on fire. Yeah, this looks a lot better. You can see the mass went down to start a little bit. But what's happened to the mass now? It went up. Not a lot, but the mass went up. It was 1.20 and now it's 1.24. That is the question I was about to ask you. Why is it going up? There's a reaction happening. It's a reaction. When things burn, they react with what? They react with oxygen. So steel wool is just iron. Iron is just Fe. So the reaction that's happening there is Fe plus O2. So the reason that mass has gone up is because we're drawing oxygen out of the air, we're attaching it to the iron, and we've created what compound? FeO. Also right there too, yeah. And if you take a look at, so here's the original. And that's what we've just made. Okay, we're up to 1.28. We added, not 1.27, we added 7 100ths of a gram. Not a lot. But if you think about what individual oxygen atoms weigh, we just added some oxygen atoms. And you can see the color here is different. When in grade 9, you look at chemical versus physical change. One of the properties that you look for to determine whether the change is chemical or physical is to see whether or not there's been a color change. There has been a color change. Here you had a kind of a dull gray color, and now this thing's blue. So effectively what we've done is we've taken that entire outer layer of iron, and we've added oxygen atoms to it. That's why the mass went up 700ths of a gram. Not overly fancy, but that's an example of a synthesis reaction. So two things, force them together. See by the change in mass that something here is happening. Cool. Next one. Let's go on Earth. Decomposition. That table. So this is almost certainly a demo you've seen before, but there really is no good reason to see it before grade 10. Because this is, it's the reaction. Everyone likes to show, if you're buying it, don't be buying it. Like at Science World, they do this all the time. They use different shapes of these produce different kinds of dramatic reactions. Oh, you've seen this one before. This is the elephant toothpaste reaction. You want to help? Okay. Who wants to help? Sweet. Good. You too. You might take this one. It's good stuff. Where did I put my games? Okay, Numbrin and Josiah, go get some goggles. Here's what we're gonna do, and you guys should slide back. Okay, so we've got our big graduated cylinder. We've got this. This is hydrogen peroxide. This is the grossest, no, that's not grossest. The nastiest thing we have in the lab. It's a danger, may intensify fire, harmful if swallowed, causes skin irritation, causes serious eye damage, may cause respiratory irritation, keep away from heat, sparks, open flames, hot surfaces. Avoid breathing mist, vapors, and spray. Wash hands thoroughly after handling. Yeah, you're back. Fantastic. Here's what I want you to do. Number one, I want you to grab this guy, the dangerous one, and I'd like you to carefully pour 80 mils in there. You get the other one. I would like you to measure out 20 mils of those. Somebody, you're close. You get this guy. Yep. Liam, you get that guy. And here we go. Got 80. 20. Okay, so hydrogen peroxide is H2O2. This is the decomposition reaction. So what you guys are going to see is the decomposition of hydrogen peroxide. Remember, you can pour that into the gigantic thing. On its own, hydrogen peroxide decomposes. It's going to sit there. You'll slowly see bubbles form, and that's the hydrogen gas being produced off of the H2O2, leaving just kind of water. Malik, make it interesting. Can you add a couple drops of food coloring? To make it interesting, Liam, would you add a few, or a little bit of actually a pretty big, yeah, you're good. A pretty big squirt of, yeah, now you're green. That's why I didn't know. Pretty good squeeze. Yeah, like that. If you don't like the fact that you're not green, I got, what is it called? Let me pass a little bit some. Pick it up, please. I'm also not green. Okay, so we've taken the hydrogen peroxide. I added some food coloring to make, Malik added some food coloring to make it look cool. And why do we have the dish soap? To make it foamy, we need something to actually catch all of the gas that we're about to produce. Now, this reaction, don't get confused with what's happening here. The reaction is already occurring. On its own, hydrogen peroxide is going to decompose. What Josiah is going to do is Josiah is going to add the potassium iodide, what this kind of brownish colored liquid is. This is not part of the reaction, but it acts as what's called a catalyst. It allows the reaction to happen faster, because this is really boring. So if you wouldn't mind, don't touch the liquid. Pour it into the big tube quickly. Let's stop it all at once and back away. And so all of the hydrogen peroxide decomposes at once. We use the dish soap to catch all those bubbles. And now we've got, and you can see it's hot, like it's steaming. It's warm. You can get close if anyone wants to. Don't touch it. But you feel the heat coming off of that reaction. It wasn't hot before, but when all of that happens together, heat's produced. And you get something, let's say elephant toothpaste. They call it elephant toothpaste because coming out of the tube, it kind of looks like toothpaste. So, you know, what's a really big animal that you would toothpaste? If you go to Science World, often they'll do this with a like a flask. It's got the big bulbous and it comes to a really thin point. If you do that, you can actually shoot this foam up to the ceiling, which I don't want to do for obvious reasons. But yeah, that's a decomposition reaction of elephant toothpaste. Thank you, the two of you. If you want to put your goggles away, you can actually give me those goggles because other people are going to do more reactions. Cool. That's elephant toothpaste. So we've done our synthesis, we've done our decomposition. We're going to save. Yes, sir. I don't know. I mean, it's steam. So it's boiled water. So anything that steams has caused a layer of water to reach 100 degrees Celsius. So that, yes, the answer to that question. The single replacement reaction, we have to go outside for. We don't have time. We'll do that one tomorrow. We're going to go to the double replacement reaction, which is this guy over here. Luis, can you grab me some paper? This paper towel over here will work this time. This one will be. I just want to wipe off Okay, next one, double replacement. The double replacement, these ones aren't overly dramatic, but they're kind of cool. So let's do this guy. We've got our big graduated cylinder. Who wants to do this one? You don't want to do open? Oh, you have already. Okay, let's do it. So I'm going to give you one of these. I'm going to give you one of these. Careful with them, as you can see, they've got danger symbols on them as well. Which one of you has the copper fluoride? Copper fluoride. You got the big tube one. You get the big one. I need you to pour 70 mils into that thing, and you have the sodium phosphate then, so I want 50 mils into that. Seven. Are you tell? We hit 70? Okay, cool. So take a look at what's here. Before we do the mixing, you can see what we've got present. We've got this kind of light blue. You can see through it. It's clear. There's nothing in there. This is, well, definitely clear. It's colorless. Angel, would you pour yours in there? So the color has changed, and I can't see sodium. So we've created a solid. Color has changed, and I'll grab the one from last block. If given enough time to sit, you can see we've got something in here. If we let that sit long enough, this is what we're going to get. You can see that there's definitely some floaters in there. And it has started to separate out. A double replacement reaction. Nothing overly dramatic. Cool, let's go over here. This is the acid-base neutralization. Put yourself in a position where you can see what's going on. So what we've got here, we've got 3 compounds that you can get at the grocery store. You can actually drink most of the stuff that we're going to use for this one. You don't want to. This is vinegar, like white store vinegar. This is not milk. It's called milk of magnesia. Oh, wow. I need to open this. Excuse me, guys. Grab my knife. And this is milk of magnesia, is magnesium hydroxide, NGOH, the base. You can buy this in the pharmacy section of any grocery store. You can see on here, actually you can buy this at the dollar store if you want. Milk of magnesia and acid, fast relief of heartburn, upset stomach, acid indigestion. It also works as a gentle, effective relief of occasional constipation. Relaxing. Both of these are consumable. This, I've mentioned it before, this is called universal indicator. So you can use this to tell you the pH of a solution. I'll show you up on the screen. This is the, right there. That is the code for the color change for universal indicator. So let's try it. This reaction is going to mimic kind of what happens in your stomach, except obviously we're not using hydrochloric acid, we're using vinegar. So I'll pour a bunch of vinegar into the beaker. I'm going to turn the thing on so it mixes it. Add some more vinegar. Okay. Okay, we're going to put some universal indicator in there, and this is an acid that's in there. So what color do you expect it to turn when I add the universal indicator? Take a look at the screen behind me. What color should it be? Yellow, red, something down there, okay? Okay, so what's the pH of what we've just tossed in there? 0, 1, 2, it's a strong acid. Okay, so now you've got this in your system, now you've got heartburn. That's a problem. So what we're going to do is we're going to take your milk of magnesia, we're going to add it to the vinegar. Take a look at what happens. Wait for it. What color did it start at? Red. What color is it now? What color is it now? What color is it now? So as the reaction happens, more and more and more of the vinegar is getting neutralized by the base that we added. Now the pH of your stomach is 8, 9 maybe, 10. We've neutralized all of the acid. We've made a basic solution, yeah. Universal indicator seems to indicate that we've changed this thing to a base. Let's add some more acid so you can push it back. Yes. What? If I hadn't put the universal indicator in there, yes. Both of these are consumable. If you were to drink them, that's the reaction that'd be happening in your stomach. Yep.
What happens if
Give you an ulcer, just because you get too acidic. Come on. Get some more. There we go. And now we've tipped it. Now we're back the other way. So now we've got a basic solution. If we can hit that kind of light green color, we'll get a basic solution. We'll get a neutral solution. Equal amounts of H and OH. Doesn't take very much vinegar to push it back. But if there's any milk of magnesia left, it will turn down. There we go. Go back to green. Okay. So we can push this thing back and forth, acidic, basic, and then universal indicator will tell us what color it is. So there's your neutralization. Then let that keep doing its thing. Okay, the last one that we're going to do today is the combustion reaction we're going to do too. So let's go over to the back table. Okay. Okay, so combustion reaction. This one is, this one's fun. We're gonna add. We're gonna see this thing stick at the last. We didn't use. We didn't start with this. So with the fire starter, all of it. Can you lift your finger? Yeah, lift your finger. Shove it in there, and now lift your finger again. What is it? Sugar. This is table sugar. I would let you do it if you were not going to be fine. This is table sugar. You don't want to do this reaction? No? Okay. This is baking soda. I'm not going to let you like this one because it would be gross. Do you want to like it? It's gross. It's baking soda. Who wants to do this one for us? Nobody wants to do this reaction? Come on, great. Come on over here, Hipparchus. You said it first. Okay, so here you go. Here you go. Here you go. I should have brought my paper over here so I can get the mouse. Get a. So you don't need goggles for this one. Yeah, no, I need no backup helpers. 1 tablespoon or 1 scoop of baking soda. Put it in the big beaker. And now 4 scoops the same size of the sugar. That's 4. No, just 4. Stir it up. Mix them all together. So you need 4 sugars, 1 baking soda. Okay? And I'd like you to pour. No, I'm going to pour. We're going to add some of this. Cool. Now we're going to pour that on top. Right in the middle. Big pile. Okay, cool. So, would you like to do the honors? Okay. Light that sucker up. Hold on. I should start by saying, this is what you're about to witness is a combustion reaction. It's not a classic combustion reaction that perhaps you would expect. Yes, I've added some fire starter in there, but you're going to see a reaction here that happens with the sugar and you're going to see a reaction here that happens with the sugar and the baking soda. That is a much slower combustion reaction. People like to say that. Let's hope it works better than the last one. Last one. Technically, yes, but you don't want it. Technically, yeah. I mean, if I hadn't put the lighter fluid in there and the beaker in there, yes. Baking soda and well, it's going to burn. And so it's going to taste like charcoal. So what you're witnessing is a combustion reaction. It's very slow. But that growing black pile is the product of the combustion reaction, the burning of sugar and baking soda. Last semester, though, last block. reaction is technically, it's a version of a reaction called Barrow's snake, because you can see you're getting these kind of snake-like tendrils growing up out of the sugar pile. And that is just a carbon block. I mean, it's just pure charcoal. And it'll just keep going. So you can see you've got these little tendrils that are growing out here and here. This big block's kind of growing. That's good. You want to get closer and take a look. You're fine. Nothing's going to explode here. Nothing's going to pop. It's a slow reaction. If you want to come take a closer look at it. We're going to let that go for a little while and see what happens. And I'd like you to move over here. Dry inside. Okay. This reaction is the reaction that where this is what you typically expect to see from a combustion reaction. This liquid that looks like water that I dumped on that pile over there isn't water. This is methanol. This is what you get when you make moonshine. You drink it, we go blind together and die. It's going to be great. So what I'm going to, we're going to burn it instead. So, methanol causes blindness. Okay, so. Seriously? Expect that crap from my right now. Okay, so this usually doesn't work as well as so we'll see what happens here. Turn the lights off. Bottom switch on the light switch. Bottom marble. If you want to film something, so if it works. So I don't know if you know this, but liquid gasoline, liquid diesel, liquid alcohol doesn't burn very well. You need to aerosolize it, which is why I poured a little bit in here and now I've been shaking it up. I've been trying to aerosolize, like create fumes that are building up in this jug for the methanol. Who wants to do the, okay. Come on over here, grab the tongs. Don't want to burn you. Put that over there. There you go. So I'm going to light this thing on fire. I'm going in this order. I'm going to remove my hand, step away. You're going to reach out and put this stick in the jug. Just drop it. Do your rest of yourself back. I hope this works. Sometimes it doesn't work very well. It's like, let me get my hand out of it. Yeah, go ahead. So that is typically what you think of when you think of a combustion reaction. I don't want to burn a hole through your shirt like that. That was a good one.
No survival instinct.
You just sit there and watches it and go,
Yeah, I just watched it. Bro, like.
so you can see in here, take a look at what's left. I mean, this is obviously this is very warm. But take a look. The products of a combustion reaction are CO2, which came off the top, the gas, and water. There's a bunch of water. Theoretically, yes. If all of the methanol is gone, yeah, you could drink that. Yes, that is H2O. I'm not going to let you. I don't know for sure that that's what's happening, but there it is. So that's the reaction that you typically think of when you think about combustion. Cool. So those are my demos for today. Yeah, double replacement separating out again. Nice, love that. Tomorrow, when we got a little bit more time, we're going to go out into the world, and I'm going to show you my favorite single replacement reaction. It's over here, but we'll do it tomorrow. Yes. Sorry? No, because it will make it harder for me to clean things up. That can't go down the drain, but that can. So, no. Okay, can you turn the lights back on? Luca? I don't know if you guys, hey, don't pack up, we got time yet. Oh, we don't have any time yet. Guys, I don't know if any of you noticed other than these ladies back here, but while we were doing this one, the snake has continued to grow. The bell's going to go here in a sec. On your way out, I want you to stop by there and take a look and see how it's grown. I am going to give you some homework for tonight. What I would like you guys to do, grade 10s, this is your homework. This page right here, classifying chemical reactions. You do not have to do any balancing. All I want you to do is, there are 30 reactions here. I want you to look at the equation, and based on the examples that we've done, I want you to tell me on this line what kind of reaction it is. You could theoretically get this done in a couple minutes. There's 30 of them, there's 16 on the front page, there's 14 on the back page. All you have to do is put the letters S, D, S, R, D, R, N, or C, depending on the type of reaction. Synthesis is two singletons that create a single compound. A decomposition is one thing that breaks into multiple. A single replacement is an element and a compound where they swap. A double replacement is two compounds where the swapping happens. A neutralization is obviously an acid and a base. And a combustion is any organic plus oxygen creates CO2 and H2O. That's your homework. When the bell goes, you may also go. Have a great day. We will see you tomorrow. I'll get tension to stuff over you. Where is Ella? Do I have any other drumliners who are going to do this tomorrow? Anybody else here on drumline going to be away tomorrow? Nope. Okay. Don't forget, guys, those questions I want you to do for homework. Those together. Everything. What are we at? I'll be honest, you watch other than me, bro. I was just trying to solve hell. Okay. Okay. You're back. Oh yeah, you went to the bathroom. Okay. Manan, good to see you. Someone told you to come see me? You just did on your own? Oh, I want to talk to you about the math contest. What's up with me on?
You said you have ideas for whatever kind of math positions you wanted for this stuff.
Oh,
I wanted a list
you wanted a list?
of whatever you think is the most important.
Oh, there are many, but I can give you a list.
And if you had any, like, are there any particular walls you want covered, or you want like all of it?
Whole area.
Alright. And do you have any ideas for like what color scheme you want? We were thinking like a scheme
Not
of
sure
like
we care.
5 to 7 colors, so it looks like uniform.
Okay.
But we wanted like, do you want like blues, warm colors, oranges? Any ideas?
I'm not sure we care. I mean, I think a white base to brighten the thing up, and it doesn't have to be totally like blocked out past that. Obviously the white can shine. I don't think we care. As far as, I mean, that's a question I think I have to ask Mr. DeVries, but where is, first of all, I need to give a few of you guys these. Okay. Where is the math contest? Okay, so Manan. That's the wrong color. Why wouldn't things be on fire in my class? If you could get this back to me by Friday, that would be lovely.
This Friday?
I know that's today's. Oh, Monday. Say Monday. Bring it back to me for Monday.
Sure.
Who else do I got in here? I got Cody. Is Guntest here too? Cody Foster. Is Jahardeep here too? Cool. That second J, I always screw up how to pronounce your name. I'm sorry, man. Ajla. Guntas. Okay, I need these back Monday. These are the release forms. These are not the permission. I'm going to give you another permission form, but I haven't made those up yet. James. I just need, is Annie here too? No.
Nope,
she's not coming back.
Bro, she's
Okay.
so done for. Like
She's back next week.
next week, she's gonna miss a whole. Oh my god.
She's literally here. Why should I go?
I mean, like I was dying on the first day when we came back. Yeah. Like I was basically.
Yeah, it's because you spent all your night playing Valorant. Hey, James, you didn't spend so much time playing Valorant.